All right, guys, let's get started. Okay, so we are recording. Audio's on. Okay. So let's go ahead and start the whiteboard here. All right, so welcome back from your break. So I don't even remember how to operate this thing anymore. It's only been a week. All right, so yeah, so this we are currently, I think, on week 13 of the semester. Okay, so we are getting ready to, we're pretty much at the end. You have no homework assignment so far, so we're kind of done with that, right? And so we're starting a new phase. Let's say like the third phase, if you remember, right? So I had said initially that I divided this class into 3 areas, which were roughly speaking the vector space model, if you want to think of it, but really you should think of, they can all be represented with the vector space model. So you should really think of this more as distance metrics. Okay, so distance metrics. All right, so things that are that have geometry, and then you can measure the distance between 2 points in a space, right? So that was the first set of things, and we'll come back to this. If at the end of the semester, I usually have like one lecture on something called clustering, and that once again, it's very similar to KNN. It's actually called K-mean, so that even the name is similar. But that's kind of like, 1.1, somewhere there, right? And then here, the second phase of the semester was all the probabilistic methods, right? So probabilistic methods that we looked at, like everything on based on Bayes' theorem, naive Bayes, hidden Markov models, and reinforcement learning to a certain extent. Okay. Okay, there's nobody there. All right, and now we're starting the third phase of the course, which is probably the most exciting to all of you, although all of these are very important as well, right? And so this is neural networks. Okay, so you've probably heard of this. You've heard of neural networks before. Neurons, you've heard of that, or artificial neural networks, ANNs, etc. And then, of course, this leads into something called deep learning, right? Which is what is the state of the art today in this field. Okay, so we are starting our discussion of this segment. Okay. The other thing, just before I forget, I want to let you know about the exam 2. So let me really quickly do that before I forget, because I'm going to be out of town that week, and so I've scheduled the exam for that. So this is the course, and if you look, mark your calendar. Yeah, April 11th, so that Monday, I'll be out of town, but I should be back on the 13th. So what we'll do is that day, you'll just have the exam. Okay, we'll do just like we did with the first one, it's virtual. Usually the exam would have been on this, which is week 12. I'm just pushing it by 1 week, okay? It's comprehensive. And then remember, we'll have 3 exams. So there's the first exam, second exam, and the final exam. They're all comprehensive. But that's actually good for you. So you've seen the exams are easy, so just, pay attention, you'll do fine. So it's not through the exams that students fail the class, right? It's not doing the homework that's the issue. All right, so anyway, I wanted to mark that, so it's already in the calendar, and you can see there, so you can plan accordingly. Okay, so it'll be just like a virtual thing on Brightspace. It'll open up during the period, the designated period. Anyway, so I did say that, so that's important. All right, so let's go back here. So neural networks is the topic in question now. And let me actually. All right, so neural networks. So let's go to a new slide here. All right, so now we are at neural networks. So this is neural networks. Okay, and in particular, artificial neural networks, right? ANNs sometimes called. Okay, so the idea is basically, historically, somebody asked a question: how do we process information? How does the brain work, right? And so they started looking at neurons basically in our brain, right? So supposedly we have neurons and they're connected and they fire and do things like that. And so then they decided, okay, we're going to try to model that artificially. Okay, and as it turns out is now this nobody says that an artificial neural network is exactly how the brain works. Who knows? Maybe our brain has some components of quantum mechanics, right? Who knows, right? I don't know. Nobody, or maybe it's simpler than we think. That could be also a possibility, right? So we assume, just like we used to think that we were the center of the universe, right? We now probably think that our brain is special, really special somehow. May not be, right? And maybe it does work like this. Maybe it doesn't. Who knows? I don't know. I'm certainly not qualified to tell you whether or not it works like that, but I can tell you that the idea comes from that, right? It comes from trying to understand how the brain works. People believe this is how, some of it works. Neuroscientists have done experiments on the brains of cats and apes and things like that, and they've figured out, okay, yeah, when I do put some electricity here and here, and something happens, right? And so they've definitely thought about it. So anyway, we will go over this. Okay, so I'll go over the theory today. I like to go over the history a little bit as well. So I'll do that. I don't know if any of you had a chance to look at those Veritasium YouTube videos. Did any of you watch them? Not at all. I watched a few. I already knew about them. You already knew about them? Yeah, so that second video was pretty good. So I don't have the fancy graphics that he had, but certainly I'll talk a little bit about the history of that as well. Okay, I just like, honestly, I just like to tell that story, right? And then it would be a great Netflix drama. All right, anyway, so yeah, so we'll talk a little bit about the history of it, the background. And then after that, it's interesting how a lot of this started at Bell Labs. Not the math, but like the implementation. And then after that, we'll talk about obviously the algorithms. Okay, so we're going to do several algorithms. The classic algorithm called the perceptron. Okay, so we'll do that classic algorithm, the perceptron. We'll do this on Wednesday. We'll go over the code. You'll see we'll implement a neural network from scratch in NumPy, right? We'll do that. And actually for pretty much everything that we're going to do in neural networks this semester, we're going to implement it from scratch just with NumPy, except for deep learning. The last part of it would not be efficient. Remember what I've always said about for loops, right? They're like your enemy. Well, it's kind of here, deep learning, they're definitely your enemy, right? So you really have to take it to a very optimized set of libraries, right? And so you guys will explore a library called Tensorflow, and in particular, the version of it called Keras, which is supposedly the simplest that you can make a deep learning algorithm, but it has the same power. It would work on both CPU and GPU, so it's definitely like state of the art. And so by the end of that, you would be able to apply deep learning to a problem. So your term project actually this semester will be that, right? So find a problem, a supervised learning problem. That means you have X and Y, right? So we're back again to the realm of X and Y. So that's probably good because it's comfortable, something you were already familiar with. When we were doing the probabilistic, right, we had to look at the problem a little bit differently with hidden Markov models and everything. They were different setups for our problem. But now we are back basically to the beginning where we model the problem as just having an X and a y, right? So we're exactly back there. So this is X and Y. The only difference is now we are applying a different set of algorithms, right? And so we're going to start to understand the fundamentals of neural networks. So we will explore first the perceptron. Then you guys have taken your statistics course already, right? All of you? Stats? Okay. So if you've taken your statistics course, you looked at something called linear regression, right? So you must have seen that towards the end. So that's great because then we pick up with linear regression. And you might say linear regression, what, how is that related to neural networks? Fundamentally, they're the same, right? So they're built on exactly the same idea, same equations, just different optimization goal, basically, okay? And so we'll see that. So the great thing about looking at linear regression is that it's very intuitive. And so because it's very intuitive, you're able to pick it up really well. And then after you've picked it up really well, then you can actually just modify it for all the other things. That's what's so great about this is that we start at the perceptron, and that leads in really well into linear regression, right? So everything builds on top of the other thing, right? So after that, we're going to look at logistic regression. Have you guys heard of logistic regression? No, right? So I wouldn't expect you to have, but as the name suggests to you, it's very similar to linear regression, but it's a variation of it. We add some more things to linear regression to make it into logistic regression, okay? So this is another algorithm. So basically this is like every week. So this is this week, next week, and so on, right? And then finally, after we do logistic regression, believe it or not, even though none of these are called neural networks, at this point, once you understand logistic regression, you pretty much understand 75%, 80% of neural nets in deep learning. So you just need that little extra to get the rest. So here then, after logistic regression, we're going to have something called the multi-layer perceptron. And that should sound familiar, correct? Where have you used a multi-layer perceptron before? The Weka homework, right? Remember how slow it was? Right, exactly. So this is where, we're back there, right? But all of this builds towards multi-layer perceptron. Here, though, we're doing everything in NumPy, so it's going to start to slow down. Okay, it's going to start to slow down. And after multi-layer perceptron, what comes is deep learning. Okay, so because multi-layer perceptron is basically deep learning with one missing piece. Once we add that little piece, which is extremely easy, we will have deep learning. At this point, though, we need a lot of computational power. And you will see why, right, as we start to talk about it. So for this is where we will explore something called Tensorflow. And in particular, in this course, in 365, I cover Calix, okay? Which is the thing that will allow you to most easily build deep learning. And we're not going to cover now. Deep learning it's actually a course by itself, right? There's many types of algorithms, many very powerful algorithms. We're just going to explore like the very basic deep learning algorithm, okay? But it's what you did with Weka, right? All those classifiers, you will now be able to do with deep learning, basically. So it's like you did multi-layer perceptron, you just couldn't do deep learning, right, in Weka. And it wasn't efficient as you saw. So this is where TensorFlow comes in because it's a library. We still use Python, but it's a library in Python that allows you now to process massive amounts of data, right? So we're talking about parallel computing now. This will run on both CPU and GPU, okay? Although we can do and what's great about it is the code is exactly the same. Like you write the code for CPU the same way that you write it for GPU. You just say, I want to use GPU or CPU. That's it. So to do this, when I talk about CPU and GPU, when I say GPU, I mean, graphics processing unit, right? So you should be familiar with graphics cards, right? NVIDIA in particular, for instance, is the dominant one for this particular task. Not all NVIDIA cards support deep learning. So you have to check, right? Like if some of you may have modern laptops which come with NVIDIA graphics cards. So you may want to check to see if your graphics card supports deep learning, right? Otherwise, what usually happens is you have to build, a rig, right? You have to build your own desktop, like in the old days, right? Mostly like gaming consoles. A lot of you may be familiar with those, right? And you probably, if you're into gaming and you have one of those, you may in fact have an NVIDIA graphics card that supports deep learning, in which case you have a very powerful computer there to do serious work, okay? Just to give you an idea, I'm currently processing a job for something I'm doing in NLP, and it's taking me 3 days, I think, 4 days. And so far, and it's not even done. It's not even like 30% done, but I'm running it on my Mac, on the laptop. If I was to run this on my GPU box, there's a speed up of five times, which is, between processing something in a week versus 1 day, right? So it's still, with a GPU, it still might be, I think the job processed in 12 hours with, on a GPU. On the CPU, it's still going. So it's very significant, right? And this is when it's, and I'm not even training, I'm just like running it. I believe that Google once ran a job in 2015 with 8 GPUs and the latest GPUs at the time, and it took them 36 days to train, okay? And that was in 2015, so things change, right? Who knows what they're doing now? But anyway, this is extremely important, right? So definitely, as you will see, parallel computing and GPUs come hand in hand with deep learning, okay? Now, when I talk about deep learning, as I said, there are many algorithms. We're not going to cover those. Those are actually, we cover those in a grad level class. So if you guys ever did like a master's here or somewhere else, those are grad level type of classes. You might hear algorithms like the transformer. You might hear algorithms like convolutional neural networks, recurrent neural networks, autoencoders, all those kinds of things, GANs, etc. So, but obviously that's outside the scope. Basically, within scope of our class is going to be multi-layer perceptron and then a multi-layer perceptron with multiple hidden layers. That's how I would define what we're doing. So we're just taking a multi-layer perceptron and we're adding hidden layers. What does that mean? That's what we're going to learn about. But that makes a multi-layer perceptron into a deep learning algorithm, okay? Deep learning algorithm. Now, TensorFlow is not the only library out there. There's another one called Pytorch. I'm actually more, I prefer Pytorch, but for this course, 365, TensorFlow Keras is probably the best one. Okay, it's not a GUI interface. It's still Python scripting, but it's supposed to be very straightforward. And it is. Any questions so far? No? All right, so I'll come up with a couple of homework assignments, but basically at this point, consider your term project assigned. I would say again, do individual projects. What will you have to do? Basically, find a problem. It has to be a supervised learning problem, right? Whatever you want it to be. It could be images, it could be text, it could be any tabular, whatever you want. Predict something. So given some features, predict some classes. Does that make sense? And find some data, and then you will run all of these algorithms, basically. We'll see, except maybe linear regression, because we'll see it's a little bit different for a different type of problem. But at the end, the key thing that I'll be looking for, obviously, is that you ran it with TensorFlow. I want to make sure that you know how to implement deep learning to a specific problem. You guys see that? Does this make sense? Okay. I'm not asking, you can just find a data set, as you guys have already proven, you know how to find data sets. You use Kaggle. Most of you use Kaggle, right? The last time around. So that's, a good place. Find something that's interesting to you. Okay. Questions about that? So that should be your term project, should be pretty straightforward, okay? So anyway, so I'll start with the history of deep learning. And then I'm just gonna get into the specifics of the perceptron. So let me go. So this is the algorithm for this week. So I'm not gonna do any scripting today, right? That'll wait. On Wednesday, we'll implement the code, and then maybe I'll come up with some tiny homework, just to make sure that you probably, like, if I give you a data set, then I'll just say, now run Iris on this. So a lot of these will be like that, okay? A lot of these homework assignments will be pretty straightforward, but certainly what's important to me, you just have like 4 weeks left of class, technically, right? Because, we're gonna wrap up and also I'll remind you, the last week of a class before finals, you need to do presentations. I don't know if I've said this, right? So for the project, this time around, well, we're still a small class, so we might do it like the last time, but in theory, you would come up here and do the talk, okay? That will be the week before finals, probably the last day or so, and then we'll have also the final exam. During finals, we just kind of virtually, as we have done the other exams. Got it? Questions? All right, so this is kind of the plan. So let's then kind of start going through the ideas. So actually, I'll start with a little bit of the history. And also, if you check Brightspace, kind of a lot of what I'm going to say, my notes are already there. Okay, are already there. So before I get into sort of the explanations of how it works, there's several algorithms that are involved in making deep learning work. Okay, so it's almost a story of how the ideas and the math was created before they could actually be implemented, right? So it's almost like, so that's why quantum computing, for instance, is a good analogy to AI in a sense, right? So, if you think currently they have a lot of ideas about quantum computing, right? They don't have the understanding of the physics complete yet. So they don't really get the physics just yet. Maybe the model, the standard model doesn't quite work or is not complete, or some of the algorithms, the math is good, but they just don't have the hardware yet, right? Because the physics is not there. And that's kind of the same story with AI and machine learning and deep learning. The ideas have been around, since the 1700s, right? So the Euclidean distance, for instance, right? Those were things that were developed many years ago for other applications, probably in math, but they were implemented for AI. And then most recently, though, the story of AI kind of, it's broad, right? Because it includes Bayes' theorem, et cetera. But if we just focus on neural nets, then the story kind of has a starting point, right? Which is when people started to think about how does the brain work, and then how do you create an artificial brain, right? And that kind of starts around the 1930s and 40s, okay? So that's basically the idea. So we'll start there. So let's do a little bit of a history. And usually what I like to do is I like to create like a timeline. Right, so this is the timeline. So it's basically around 80 years. Okay, and it's important because you should understand the context of the history of AI to really make you understand why, right? Why is it that this is so important, right? So we can say, for instance, before, obviously, there was all the math, right? So the Euclidean distance, Pythagoras, etc. But around the 1940s, you have somebody named Rosenblatt. as I said, today I'm going over the little bit of the history. So Rosenblatt is really one of the first people that you want to, that started this, right? So there's a few people there. There's always several people that work on something, but Rosenblatt, he worked at Bell Labs. And, a lot of the digital age that we enjoy today, right, came from Bell Labs, right? So famous people like Rosenblatt, the people that invented the transistor, was Shockey, I think, or something. Can't remember their name. And then there's also Claude Shannon, father of information theory. So all these people worked on different aspects of this, and of creating the digital age, basically. All right. So, but definitely Rosenblatt, he is at the beginning, and he's this is where the perceptron comes in. So it's this idea of how do we model neurons in the brain, right? So could we create a computer? Remember, in the 1940s, you didn't really have transistors even, right? So the transistor had not been invented. So you were talking about tubes, right? Those vacuum tubes, et cetera, relays, et cetera, as they were building things. Another person that was really important around this time, but that I've mentioned a couple of times, is Claude Shannon. So Claude Shannon, to me, is somebody that's like Albert Einstein, but just doesn't get the credit that Albert Einstein gets, right? So Claude Shannon obviously proposed information theory, which is, pretty much everything. He actually is probably one of the first people that used the term bit, those kinds of things, measuring. You've taken this, I'm sure, when you took your 170 class or 270, you learn about the network, right? And you learn about transmission rates and all that. And that's really the problem that he was working on, because he was working for Bell Labs, right? The phone company. So they wanted to find out the noise, the transmission of information, et cetera. How much encoding do you need to send a semantic message over a channel, right? So that's Claude Shannon. But Claude Shannon did this, and Claude Shannon is like a genius who invented this, and then was so bored by everything, right? That, after doing something like inventing a whole field, he also decided to just entertain his intellect by playing with artificial intelligence, right? So I think I told you this before, he did some of the initial work on what we could call reinforcement learning, right? We learned about this in a mechanical way. He created a robot maze, a robot mouse. He's not I didn't say he was the founder of reinforcement, but he's the founder of information theory. But he did work on, he became interested. He was like a very eccentric person, right? So he worked at Bell Labs, and then basically they just let him sit in his office and do whatever he wanted, right? And the only thing they asked him to do is keep his door open so people could ask him questions. And then this is true, he would through the hallways of Bell Labs, he would ride a unicycle. So he became obsessed. He was like a very obsessive person. So he became obsessed with mastering the unicycle, the one wheel thing. And so imagine just, he would run through the hallway on his unicycle. So it's a true story. I'm not making this up. And so he's definitely an eccentric person. But he would also become interested in things like creating a robot maze. This robot maze that he created is now in a museum, right? And it worked. Like the mouse eventually learned how to find the cheese in this mechanical environment. So he was, pretty smart. This is around the 1950s, right? That's Claude Shannon there. At the same time, there's an algorithm called Adeline. We will not cover that one, but that historically happens around this time. It's a development from the perceptron. Okay. Then we have basically Rosenblatt created this idea, right, of the perceptron, and he kind of proved it, that it works. And it was very simple. if you want to think of it of a simple way, imagine that our brain has neurons. So he just created one neuron, right? That's kind of a good analogy. Imagine of a brain that may have trillions of neurons. I don't even know. This was one neuron, the perceptron, right? And so people became very excited in the 1940s because they thought, okay, with this, we can do anything. Then there was some people, Marvin Minsky and some people, and they basically did some work, theoretical work, and they proved that there were limits to the perceptron. So it's kind of like they said, no, it's not going to work. So then, so what has happened, this is important actually, what has happened with the story of AI is that it's like that. It's got moments of excitement and then boom, it falls, right? So these are called the dark ages of AI, right? So periods where we hit a limit and then people say, well, there was a lot of excitement, but no, this is not going to give us true AI, right? And so you can see how it started in the 40s and 50s with Rosenblatt. Then Minsky came in and he kind of like ruined the party, right? So, and their ideas stayed pretty much. When I was doing my AI studies, Minsky was still, a problem, like a wall that people would tell me neural nets are not the way to go because Minsky back in the day said that there were, it couldn't solve problems, it wasn't feasible, etc. You guys see that? So that's the story of it. So Minsky kind of, as I said, ruined the party. And so a lot of scientists who were excited about this, a lot of places decided, no, we're not going to continue doing research in AI. And they just abandoned it. But there were some people that were just like, these people that just continue, they were very persistent, they just loved the field, and they kept working. So so we're now jumping to around 1986. And here we have Geoffrey Hinton. And Geoffrey Hinton in the 1980s, 1986, was working on AI. Neural nets, nobody likes it. They actually, they weren't laughed at, but almost, it was that kind of thing. So if there was a conference, they would have like a special table for the neural network people. That's how bad it was. I'm not kidding. In 1986, people would just not appreciate it, and they thought that these people were wasting their time. Question? Specifically because Minsky, well, he's a very brilliant guy. And so he did like a theoretical proof that neural nets were limited, that they couldn't solve problems, etc. And other people, I'm sure, contributed to that. It's kind of like, somebody says something and then a lot of people start working on that. Yeah, he had a following, yes. And these are like, so the problem with neural nets is that they're almost like a black box, right? Sometimes it's not very clear what's going on. At least back then, it wasn't very clear. Whereas statisticians and mathematicians have a tendency to dominate everything, and they think they know everything, right? And so it's true. And so the problem is then they prefer things that are like mathematically beautiful, right? So very perfect mathematical things. And neural nets aren't exactly like that. They're just like a simple machine that just, it's like a very, very strong hammer. You know what I mean? It just, with a lot of iterations, it learns, right? And that's not something that they liked, I think. They wanted something that was theoretically very perfect. And so they had a tendency to gravitate towards that versus neural nets. But it really affected this period in time. Minsky really affected the history. And I'll read to you guys a little thing. I brought a couple of things that I'll read to you about the history. But anyway, I like to tell the story, kind of like this. So the point is, Geoffrey Hinton, a few other people, Williams, forget his first name, and Rummelhart. They were just imagine they were at the AI conference, they were the three guys that always sat together, and they were like in the kiddie table in the back, right? So not very much appreciated by the other people who were doing exciting things with Bayes theorems and everything like that. But regardless, and also there was no computing power to solve these problems. Computers were in 1986. Think about the computers that we had, right? So we had what? Atari, and we had the Apple II, or something like that. So not very powerful, right? So really, we couldn't really solve this. We could barely use the algorithms that we had. But Geoffrey Hinton and people like him continued to just do research. And they continued to explore the problem of neural nets and how to train them, how they should work. And so they came up with a set of algorithms. There's about 3 algorithms that make neural networks work, and I'll list them in a second. One in particular is called backpropagation. Backprop. This is an algorithm, right? So to implement a neural network, you have to have 3 techniques, right, that help you. So very much like I said, for instance, remember when we did hidden Markov models, I said, what was the algorithm that you needed to use for that? You guys remember what I said? The Viterbi algorithm, if you remember, right? I gave you the Viterbi, but we didn't go into the specifics of it. It uses dynamic programming. So just like that, neural nets need a set of algorithms to solve a neural net, to make it work. And so these were basic ideas. But the interesting thing is there was a guy, Samuel, I think, something. He came up with the original idea. What you need is you just need data, and then you give the data to a model. The model predicts, and then compare what's predicted to what is the actual data. Measure how far apart those two are, and then based on that, kind of update the parameters in the function that generated that data. Do you guys see that? So it's like, that's it. That's deep neural nets, right? So you basically have a model, give it some data, it predicts. Is it good? No. Go back to the function, change the weights, try it again. Does it work? No. Go back. If we had a quantum computer that can do billions, we wouldn't even need advanced algorithms. We could just try all of them at once and get the one that works the best. But we don't have that, right? So the next best thing that we have is, our CPU, GPU machines. They take much longer, so that we need strategies to pick the weights. You guys see that? And those strategies are these algorithms, backpropagation and so on. Got it? But at the end, there was at the very beginning, there was this idea put in words. It wasn't even put in like equations or techniques, just in basic words. And that same idea is what we use today. It's just over 80 years, it has been modified, right? And has been improved. And even though a lot of people got out of this field, as I said, Geoffrey Hinton and all these people kept working on it around the 1986. Geoffrey Hinton is a character. He's a British fellow who moved to the US first. And he was doing research here, but a lot of the work he was getting was for defense. And he's a pacifist, right? So he didn't want to work on that. And so he moved to Canada, where he could just apparently in Canada, you can just do whatever you want. So he started working on the same thing, but not for defense. And then he kept working on this. He's at the University of Toronto still to this day. There's a funny anecdote about that. He's called the grandfather or the godfather of deep learning. So that's a nice title. It's also very nice that when he became famous, and as I said, I'll share the story. I only do history today, but I got to tell you this story. And so Geoffrey Hinton, actually, I love this part. When he became known to the world, right? When deep learning became known to the world, Google basically said, we got to have Geoffrey Hinton. So they went to him, they offered him a ton of money, and they asked him to move to Silicon Valley, right, to California, where they are. He said, no, I mean, he's an older guy, and he's at the University of Toronto, and he just said, no. He also has a problem with his back, I think. And so he didn't want to move. He was very comfortable in Toronto, when Toronto was just some nice place, but there's no Silicon Valley there, right? And well, Google then just said, okay, so if you're not going to move here, we're going to move over there. So they literally created a Google facility in Toronto for him. And he said he was going to continue to just work at the university. So they're like, fine. And now he's at Google, but they got him. But you can see how from there now, if you look at Toronto in Canada, it's actually like the second or third Silicon Valley in North America. I think it's California, Austin, Toronto, and a few others like New York, et cetera, Seattle. But, all because of that one person, right? So it's pretty interesting. And all of his like students at University of Toronto, et cetera. So it's definitely a nice, interesting story. Anyway, so Geoffrey Hinton just kept working on this, kept being relegated, right? And not really appreciated, to be honest, but he kept publishing the theoretical work. They would experiment as much as they could with the computing power that they had, but they were just, the hardware was just not there. So this takes us to around 2000. It's funny because I graduated actually in 2011, just before this happened. And I'll tell you this honest story. I finished my studies without ever knowing about deep learning, even though it was already happening. And this is the reality of the world. These are the things that you guys should learn, that just because we don't know it here, it doesn't mean that it doesn't exist somewhere. And so you have to keep your eyes open, because I finished in 2011 my studies not knowing anything about deep learning, but also Google didn't know about deep learning, or Facebook, right? It wasn't known to the world until 2012. This is the official date, the singularity, if you will, right? Where it just became like this rush. So if we looked at AI as a graph, like if we looked at it as a graph, you would basically see like this, and then in 2012, it jumps, right? This is what happened. And so the story is also very interesting here. And it actually doesn't, not in 2011, in 2012, right? So it would have been 2012. So I missed it. I had to learn it after. So, and that's the reality of life, right? So, you guys are learning all this stuff, and maybe the really important thing in your careers will happen 3 years after you graduate from school. So just be ready for that, okay? But so what happened? So the story doesn't start in 2012. It actually starts in 2007. This is the critical moment, okay? Because what happened was, one example of this, like my advisor, when I was a student, he graduated in 92. And he did some work in AI and in neural nets at the time as well. The hardware was not there, but he was kind of in the cloud of Minsky. So when I was a student myself, I brought up neural networks, and I was just completely discouraged from using it, except to kind of use it as like we did in Weka, just throw multi-layer perceptron in there. That's literally what I did back then, right? And I was discouraged from, and I'm not saying that, that is my advisor's fault. It's just the mentality. And this is important because I'll read you a little story it's called Perseverance or something like that. And it's very important. But anyway, a lot of brilliant people just didn't keep up with it. Only people like Hinton, but see, the people that keep up, those are the people that get facilities built around them, right? Because they just kept doing it. So anyway, so what happened is Hinton and other people, their students, kept working on this, right? Kept creating the algorithms. As I said, they kept coming up with the solutions. They were like, well, to do this, if we use this algorithm and this algorithm, I think we could solve it. And they had some computing power, and they were trying to do like tricks to get things to work, but still the hardware was not there. You guys see that? That was the frustration. And then came 2007. In 2007, something pretty amazing happened, right? So in 2007, we get NVIDIA, this company. And they weren't trying to solve machine learning or AI. What were they trying to do? Gaming. So they were trying to, all in parallel to all of this AI stuff, in the 80s, we've got what? Atari, Nintendo, Sega, whatever, all those technologies, right? And eventually PCs. And then, you know, we were playing Flight Simulator in the 90s on PC, etc., right? And then in 2007, we get GPUs, right? And this is the key thing, right? So this was the game changer. So we have GPUs for video games, which bring us parallel computing. Now we can process things in parallel. And you might say, why is it, you know, why is AI and gaming, why are they related? As it turns out, and I'll show you, I'll go to this. Video games and AI, basically, in terms of the bottleneck, they basically have the exact same problem, a matrix multiplication. This is why this class emphasizes so much, right? We started with the NumPy matrix multiplications that you guys did. Remember that? Because that is so fundamental to being able to do things, okay? Why? If you have, in video games, you have a mesh, right? You have a mesh. So a mesh is basically what? A whole bunch of points in a space, right? You know, like I want to render that chair over there. So I need to know, you know, that's made up of, let's say, 10,000 points. Each one of those points is just X, Y, and Z, correct? You guys see that? Right? So each one, so what do? I render, you know, like that, right? So a simple way. So I, you know, all these points, all these points, all these points, and I need to know all the X, Y's, and Z's. So really, a mesh is X, Y, and Z, and all the points 1, 2, 3, all the way to 10,000. Let's say. Do you guys see that? What is this? This is an X of size n by 3 in this case. You see that? Now let's say that that's a ship, right? You know, like flight simulator or whatever. I want to move the ship in that direction, right? What do I need to do? Every point in that axis needs to be added a little bit, right? You add a little bit to it, to every single point. So what you do to that, whenever you want to, in a vector space, whenever you want to move a whole mesh, you just multiply it times some vector. Okay, that's it. So that you can process everything and move it. So it's a matrix multiplication between X and something. Let's call it, you know, W. And that gives you the new mesh. You guys see that? So it moves it. Well, in machine learning, you guys already know that we have the X. We want to get the Y, right? Because we want to predict that. And so we need the exact same thing, a set of weights that if we multiply the data set times that, it gives us the predicted value. We're all familiar with this equation, right? What is that equation? Slope, right? The line equation, perfect, right? So I give it an X times some kind of value here and it gives me the Y, right? So this is the, you know, in a space, this is a line, basically. You see that? That's the exact same thing that happens in a video game. You see that? And so NVIDIA created these graphics cards that were in particular very good at that. GPUs are not CPUs, right? CPUs are sequential. They have all these registers. They do all this stuff, a lot of things. GPUs only do one thing, matrix multiplications, but they do it very efficiently. Why? Because in a CPU, you take that mesh that has 1 million points. You got to do the first one, second one, third one. So your video games would look like this. Imagine if every time it looks like this, right? That's not good. It's not fun, right? So what do you need? You need to multiply all points at the same time so the thing looks seamless. You guys understand that idea? That's what the GPU does. So it turned out that's exactly the same thing we need to do in machine learning. And so, you know how it is, the NVIDIA people, maybe someone at NVIDIA thought about the AI thing, but they were just driven by the money, right? Of solving this gaming problem. But as they started to flood the market with these graphics cards, then somebody probably that like AI and video games started to think, wait a minute. This thing does a matrix multiplication. This is the thing that I've been waiting 30 years for. You guys see that? And so that's what happened is if I go, so hopefully that, you guys, is that clear for everyone? That's it. And it's pretty fundamental. And so, like I said, that's why this is an important, it's important to understand the context. So in 2007, then now we have GPUs, right? And then the people like Hinton and team just saw this as, okay, what is going on here? And then they started to implement the code on this GPU. Now, programming in parallel is not like programming for CPU. It's very different. It's very tough. Okay, you do this. Initially, they did this in C, C++, and they needed a library called CUDA, which is the NVIDIA library for dealing with the graphics processor. And this is not fun. I mean, this is really tough. That's why today we have things like TensorFlow and Pytorch, which make this seamless. We don't actually program in parallel, right? You know, the library in Python abstracts it for us. We have to still think a little bit about parallel, but not as if we were implementing this in CUDA and C++. Got it? Does that make sense? And so in 2007, what happened was they started to play with this and to do research, okay, on image processing. They started to process images, the classic example, you know, of processing images. And as it turned out, every year there was a contest. I think it was called the Imagenet contest. And basically what I think it was like 1 million images they put together by a team, 1 million images with multiple classes. So it had like cats, dogs, but it had like a buses, cars. So it's several different things, right? And so you were supposed to build machine learning algorithms. You would go to this contest every year. Everyone would present their algorithms, and then they would give a prize to the best one. So everything was pretty normal. Let's say between 2007 and 2012, the performance, let's say, was around, let's say 60% on this. So they were doing okay, but not great, right? For a multi-class problem. In 2012, this is when, that's why I said this is when it became known to the public. The team, I think it was Jeffrey Hinton and their team, something called AlexNet, I think it was called. I assume Alex was the main person that worked on this, probably Jeffrey Hinton's student, I think. They entered the contest in 2012 and they beat everyone. And they were at, if everyone, I don't remember the exact number, but I believe everyone was around 60%. They were above 75%. So it was a significant jump in performance. Okay. And that really caught like they just beat everyone. And that then everyone wanted to know how they had done it. And then they were like, oh, we use deep learning. And then this is where, and how did you do it? And then, you know, we use GPUs. And then this is where they became extremely famous. And this is basically where deep learning kind of started, because at this point and after this contest, it just became like everyone had to have this knowledge and these techniques. You guys see that? So this is basically, they won the contest, right? And this was the University of Toronto, right? So they did this work. And then after that came, after that is just Silicon Valley basically got on board with it. Around 2015, so during this time, everyone was using C, C++, CUDA. Even myself, I was like struggling with this, right? You know, very frustrated trying to implement this in this. But then in 2015, Google released something called TensorFlow. And TensorFlow 1, and I liked TensorFlow 1. It was nice, actually. Then came also a little later, I think, came something called Pytorch. This was basically by Facebook, right? So they were kind of leading that effort. But these two libraries, and there's a few other ones out there, made deep learning accessible to everyone. Like if we still had to use CUDA, we probably wouldn't have this class, right? At least for the deep learning part. But given that we have TensorFlow and Keras, now it's accessible. It's that simple. You guys see that? And so that's basically in 2012. We get this around 2017. We in between 2012 and 2017, somewhere around here is like something called the CNN, Convolutional Neural Networks by Jean LeCun. He pioneered some work that's really important. And then we've had a lot of algorithms. As of 2017, the most powerful to date is called a transformer. It uses something called the attention mechanism. This is kind of where we are right now, as far as and probably there's something somewhere, as I said, that we just don't know about yet. So in 2-3 years, there might be something, I don't know, some other algorithm that's going to be even better than this. But this is kind of where we are, okay? And that's basically the story of deep learning. Does this make sense? Any questions? Yeah, go ahead.
Did you want to mention the other two algorithms?
Oh, yeah, that's right. That's right. So the algorithms are actually, so if you think about the problem, right? And we'll talk about all of this, especially when we go over the code. There. That's a good point. So during this time, right? So during the 1986 period, this period here, neural nets was an idea, but how do we solve it? How do we implement it? And this is where we get some of the algorithms. So to solve deep neural networks, we got the following. We needed the feed-forward algorithm. Then we've got the back propagation algorithm. And then we have something called gradient descent. These three are basically the three main algorithms that made neural networks work. Feed forward, as it implies, is just, you get some input, you go to the output. Once you get the output, then we need to back propagate. Once we compare the predicted result to the real result, so that we need to go back, and that's called the back propagation. And then there's the algorithm called gradient descent, that is the one that updates the weights. So we'll look at all of this, but these are the three algorithms, the names of the three algorithms that make this possibility, and these are the contributions of Jeffrey Hinton and all of them. I believe one of these was created, there's a paper where they pretty much laid it out. It's never like they just invent out of nothing. It's always incremental, right? But they're basically the ones that made the thing that proved it worked or something like that. You guys see that? Does this make sense? All right, so before we, yeah, go ahead, please. Back propagation. So basically, without getting into too much, right? We have some inputs, we predict some outputs. You guys see that? And between it, we have to define the neural net. This is the thing that we still need to learn. But we need an algorithm that takes these inputs and gives us that. That's called feed forward. Once we get here, we predict the value, let's call it y hat, and we compare it to the real value. Do you see that? And then we just say, is it similar or very dissimilar? Based on that information, we back propagate, which means we go back. Why do we go back? Because here is the key. You see, we need to modify the parameters. This is a thing made up of parameters. It's what is called an architecture made up of parameters, which are called weights and biases. But we'll look at this in a lot of detail. Does this make sense? And then there's gradient descent, which is the actual technique that we use to modify the weights, basically the parameters themselves. So we'll talk about that as well. Got it? All right. So anyway, so before we get into all of that, just want to finish with some little information. Yeah, so actually it was back propagation, this one, that was created by, so you can look up the paper if you'd like. So this was published in Nature, which is like one of the best journal. Nature 323, 6088 in 1986. You can look up this paper. I'm pretty sure you can find it. This is a paper by Rummelhart, Hinton, and Williams. And this is basically what cemented them as, fathers of deep learning, because this is one of three that makes all of this possible. Okay, got it? All right. So that's kind of the little bit of the history. And then let me just make sure. Now, the very first problem, as I said, that was tackled with deep learning was images, right? So remember, Imagenet. So it was a classification problem for image recognition. And then I just want to kind of go over a few additional things. So yeah, so Rosenblatt, they came up with the original perceptron. And here's the little piece that I didn't tell you about, so I'll kind of read this. So in 1943, McCullough, a neurophysiologist, and Walter Pitts, a logician, teamed up to develop a mathematical model of an artificial neural network in a paper called A Logical Calculus of the Ideas Immanent in Nervous Activity. So as I said, this is kind of where the thing is starting to be created. Then we have Rosenblatt. Yeah, so then this idea was taken up by Frank Rosenblatt, which is one person I mentioned here. You can see, building on their ideas, further developed the artificial neural network to give it the ability to learn. Right, so that's why I said Rosenblatt is really where a lot of people start, because whereas the other ones were kind of just theoretical in their idea, Rosenblatt is the first one to try to implement. So even more importantly, he worked on building the first device that used these principles, which is called the Mark I perceptron, okay, which is the algorithm that we will discuss on Wednesday. He wrote something called The Design of an Intelligent Automaton. And in that work, Rosenblatt wrote basically, we are now about to witness the birth of such a machine capable of perceiving, recognizing, and identifying its surroundings without any human training or control. The perceptron was built and was able to successfully recognize simple shapes, right? So there was a lot of excitement, right? But then an MIT professor named Marvin Minsky, who's the villain in this story, who interestingly enough, who was a grade behind Rosenblatt at the same high school. This is how it was back then, right? Everyone just went to the same school. Along with somebody called Seymour Papert, wrote a book called Perceptron about Rosenblatt's invention. And basically, this is probably the question you guys had. They showed Minsky that a single layer of these devices was unable to learn some simple but critical mathematical functions such as XOR. You guys are familiar with the XOR problem, right? And they just basically prove that. You say that this thing is very intelligent, right? That's kind of, think of it this way. Rosenblatt, very excited. They're like, oh, we can detect images. This is going to revolutionize the world. It's going to be the next human, right? Human level intelligence. And then comes Minsky and says, oh yeah, solve XOR. Couldn't. You see that? And so they show that a single layer, now notice that it says a single layer, right? So neural nets are, that's why they're called deep, because they have multiple layers. They don't just have one layer. And we'll see what that means. They showed that a single layer of these devices was unable to learn some simple but critical mathematical functions, such as XOR. In the same book, they also showed that using multiple layers of the devices would allow the limitations to be addressed. Unfortunately, only the first of the insights was widely recognized. Think about this. They weren't even saying that it couldn't do it. It's just like it was a misinterpretation, where it's almost like, it's like marketing, right? You say, oh, it can't solve XOR, it doesn't work. You see that? Even though in their paper they showed that using multiple layers of the devices would allow these limitations to be addressed. Unfortunately, only the first of these insights was widely recognized. As a result, the global academic community nearly entirely gave up on neural networks for the next 2 decades. All right, this is the story. And then there was the work by Rumelhart and somebody named McClellan as well. Okay, so then, so that's Rumelhart is this guy, right? So Rumelhart and Hinton. So they kept working on it, and basically then, and that's the rest of the story. Okay, but that was something I wanted to say. And then the last thing, and I'll wrap up with my history talk here. But there's something very interesting I wanted to mention. So little things called tenacity and deep learning. So this is a lesson actually, because I've actually experienced in the sense that, as I said, my advisor, who's a brilliant person, gave up on it too in 1992, even though he was working on it, right? And he gave up on it, and he was my advisor, so then I wasn't part of it either. You know what I mean? So it's kind of this thing that, and it's all been because of lack of tenacity, I guess, or lack of courage. So let me tell you the story. So the story of deep learning is one of tenacity and grit by a handful of dedicated researchers. After early hopes and hype, neural networks went out of favor in the 1990s and 2000s. So there's been several periods, as I said, which are called the dark ages of AI, or the winters, right? They call them, right? So they have happened with Minsky, and then around here again. There was excitement around the 90s with Hinton's work and Rumelhart again, but then again it fell, right? So after early hopes, neural networks went out of favor in the 1990s and 2000s, and just a handful of researchers kept trying to make them work. Well, 3 of them, Jean LeCun, Joshua Benjamin, and Jeffrey Hinton, were awarded the highest honor in computer science, which is called the Turing Award, which is generally called a Nobel Prize in math, right? There's no Nobel Prize for a computer. All right, and 2018, because after triumphing, despite the deep skepticism and disinterest of the wider machine learning and statistics community. And it's, they tell the story, as I said, that they would go to conferences and they were relegated to like the back, and they were somewhat of a joke, honestly, right? So, Hinton was told of how academic papers showing dramatically better results than anything previously published would be rejected by top journals and conferences just because they used a neural net. So it almost became this thing that neural net math, we don't even care, right? And look at how important they are today. I mean, companies like Facebook, Google make billions of dollars, right? And that helps them. LeCun's work, Jean LeCun, who is now I think he's the head of AI at Facebook, did some work on an algorithm called convolutional neural networks. And he showed that these models would read handwritten text very well. So he built a system, one of the first useful systems for the post office. So you know how you guys, or we all, when you write a letter, we put in the zip code and it's handwritten digits, right? Your zip code here, whatever, 46323 is Hammond, I think. And so what they wanted at the post office is they wanted a camera to sort the letters based on zip code. And because it's all handwritten digits, Jean LeCun, who is actually a famous person in AI, is famous because he built that system, one of the first working systems for like industry or the government. It worked, right? And still though, AI wasn't getting credit, even though it did work. Okay, so that's so basically the last, I'll kind of conclude here. So there's a lesson here for all of us that you want to have perseverance, right? So hopefully you get the story now. Some people just kept at it because they loved it, and actually it turned out that they were rewarded for their work. Does that make sense? So hopefully that's important. I usually don't do history and things like that, but I feel the context of AI is kind of important so you understand why you're doing the things that you're doing, why appreciate GPUs, etc. That's why I always give you that multi-layer perceptron homework also, so that's like ingrained in your brain, right? That you got to be efficient. Does that make sense? All right, great. So now I'm done with the history lesson. So now let's go ahead and just get started with the algorithm itself. So now we're going to take a look at some of the fundamental ideas of deep learning. And then, as I said, we'll look at the very first algorithm, the perceptron by Rosenblatt, on Thursday. Okay, so now we're going to get into deep neural nets and their background, basically. All right, so what is the original idea of Rosenblatt? So this is called the perceptron. So we'll start here. So we've got the perceptron, and we really have to think about the brain, right? So if you think of a brain, you've got like neurons, right? And the neurons are connected, and then somehow there's like current, right? Some kind of electric current. And then maybe this is tied to our eyes somehow, and our eyes see something that hits a neuron, and then something happens that ends up somewhere, right? So that's kind of the idea with the brain. Okay, so then Rosenblatt, so now you understand who he is, at Bell Labs, started working on this problem, and he basically came up with an idea for implementing what is called the perceptron, which is a binary classifier. It's a binary classifier. Okay, so the way it works is, you guys remember that we're in the realm of X and Y, right? So we have a data set with features and samples, right? Just like before. So this is n by m, and then this is n by 1, right? Where we have the labels associated with each vector of features. You guys remember that. So just think iris, for instance, or something. So then the model that tries to mimic this neural in the brain is basically to have something like this. So we're going to say, 1, a value 1, and actually, I'll just do it like this. 1, x1, x2, ... xn. So now we're going to think of this as neurons. And what are x1 and x2? They're just basically the features in the samples. Okay. So for instance, if we look at iris, You guys should remember that data set. What did we have? We had 4 features, F1, F2, F3, F4. What were they? Petal width, petal length, sepal width, sepal length, right? Measurements of the plants themselves. And then we had the samples. Do you guys remember that? Well, then, in this case, we would have 4, right? So here, although I generalized to n, it would be 4. Each one of these neurons represents an input. So we grab this, and then we feed it here, right? And each of the features in the vector is basically an input. So here is F1, F2, F4. You see, they become, for each sample, so it's like we grab a sample, we throw it into the input. This is called the input layer, okay? And that's why we're talking about layers now, because everything is going to be like sequences of layers like this, okay? So this is the X example. And then Rosenblatt said, well, we can take all the inputs and just arrive at one single point where all of them are added together, the sum of all of them. And so they're basically tied here. So they're connected. You guys see that? But before, we don't just take inputs and add them together, because then there wouldn't be any change to them, right? You know, we would always just give it the inputs and they would be added here. So we need some way of adjusting them. And what we do is we will take all the X's and multiply them times an associated weight. You know, so this is going to be then, we can call this one W0, W1, W2, Wn. So what this in essence means is it's almost like this, you know, you look at, you're buying a car. Let's say you're buying a car, right? So what are the things that you think when you buy a car? Speed, gas economy, horsepower, you know, also if you like it, if it's a 2-door, 4-door, you know, that kind of thing, right? Price, you know, all of these variables. But then, which of those variables are most important to you? Let's say you, Lenny. Which one of those is the most important? Gas. Okay. How about you? Horsepower. You see, so you're both different. That's good, right? So whereas X1 might be gas economy, as he said, for you, it's horsepower. So your 2 models for making a decision about buying this car they all have the same inputs, but they're different. You see, the AI model that is built for you, the perceptron, would do what? For horsepower, it would give it a higher weight. You see that the weight here would be like, you know, should be close to 1 if it's extremely important to you. Whereas gas economy, how important is that to you? You don't care? You'll have a V12? Sure, why not? Right? So then that's almost 0, right? Very low. Whereas for you, Lenny, you don't care. So you'll have a 4-cylinder, right? So then for you, F1 would be very high as a weight, almost 1, but the other one might be 0, right? Do you guys see that? And then for someone else, what if both of them are important? Both horsepower and fuel economy, right? So then you need to settle maybe on a V6, so, right? Something like that. What would happen to the weights in that case, in your opinion? What should they be? Right, so maybe just thinking about a number, 0.5 for both. Why not, right? So they're both kind of equally important. So then the weights get adjusted for that. Do you guys see how it works? Now the architecture does not change. It's the exact same architecture. The inputs are going to be the same, but your outputs are all going to be different based on what you want. So the classifier here would do what? Would predict if you want, you know, fast car or you want a fuel economy car or something. You guys see that? That's the basic idea of this. Okay, that you have some inputs. You have some inputs, the X's, which represent whatever variables could be for buying a car or iris data set or pictures of a cat or dogs, whatever. But you take these inputs, multiply them times weights, and then you add them. Okay, and that is called a linear model. It's still not a neural network. It's just a linear model. But that was the original. Rosenblatt started with this idea, right? Thinking that that's how our brain works. Our brain also has. So think of this. Would you say you have do you think you have neurons in your brain? Are your neurons linked by something? What is that called? Who knows, right? But they're connected, right? Now, the question is this. Are these connections changing? Huh? You think it's all hardwired. You have like 1,000 neurons, they're already connected. It's not like a connection is being, like a little thing that goes to a neuron and then to another neuron. It might be that they're all just connected, but somehow something about them changes in the connection. So what I'm saying is, do you think we have something like this in our brains? Or do you think we have something where that happens? This one? Yeah. All right. So I don't know, honestly, right? So it could be. So for instance, in Alzheimer's, what happens is apparently you have this, and then eventually that goes away. And that's why you forget this, right? So, according to my understanding. Again, this is not the class is not about this, but in terms of how this works, right? In terms of how a neural network works, the assumption is the brain is hardwired like this. The connections are already there, but you can somehow adjust these values, these weights, very much in the way that we said this would happen. You guys see that? This is extremely important because at the end of the day, a neural net is just the weights. You build some architecture that's just saying like you build some brain, but the values are all blank. And then you need to train it to fill in all those values. Do you guys see that? Is that a clear concept? Do you have any questions? No? All right, so anyway, that's the original idea of Rosenblatt, right? But this is not done yet because this is a linear model. So you basically do this, but then you need to do something additionally here, right? So sometimes this is, now in the original algorithm, Rosenblatt didn't necessarily introduce what is called an activation function, but there was some kind of a function that was called a threshold function. And what that function basically means is you take all these inputs, multiply them times some weights, that gives you a value. And then with this value, you need to decide what to do. Basically, that's why it's called the activation function, which means does it activate or not? So a simple way of understanding this is if this is all inputs like this, and then we map this to a value between 0 and 1, then we could say that the threshold is 0.5. So anything, whenever we get a value above 0.5, it fires, which means it gives you class 1. If the value is below 0.5, it doesn't fire, doesn't activate, so it gives you a class 0. Do you guys understand that? And now we have a mechanism to create a binary classifier. You guys see that? That's it. This is all there is to the perceptron. This is what we're going to implement on Thursday. Okay. And then after that, you get, so this is, I'll just draw this kind of like this function. This is usually referred to as the sigmoid function. Doesn't look so great, but should be the sigmoid function, which is a activation function. And there are several ones that are used. You'll see this is what gives this the power of going from what is called a linear model to a neural network, a nonlinear model. And nonlinear models are the ones that can, in theory, solve any problem. Okay, not the perceptron itself, but the extension of the perceptron. So think of the perceptron as like the great-great-great-great-grandfather of deep learning, but it's all built on this initial idea. Is this making sense so far? And then, of course, you're going to have the output here, the output, and then the model, of course, has this idea of modifying the weights, adjusting the weights. And that's what we're gonna, one of the things we're going to explore. So in terms of this, then this can be represented as a formula, right? Which is a linear formula of what we had before, x1 times w1 plus x2 times w2 plus dot 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 x xn times wn. Do you see that? So if we go back, think about it. We take xn times wn plus x2 times w2 plus x1 times w1 plus, and then 1 times w0, which is usually called a bias value. Okay? But it's basically just a linear sum that gets us to this point here. So it gets us to this one over here. All right, so if you think, then this gives us y. Is this intuitive? This is called a linear sum, so this is a linear model. It's linear because it doesn't have things like x squared or x cubed. It's not a what is called a polynomial or a quadratic function. You probably remember the quadratic function, right? You saw that one in school. X2 plus x plus b, right? It's something like that, right? So, and then you learn some things about how to make this into two equations and all that. But those represent actually shapes. So if we want to plot functions like that, whenever we have a quad, oops. Another thing that we can think of is, sorry, that whenever we have functions, this is what I want to do. So whenever we have functions, let's say we have a function like this, x. Now notice, I don't know if you've made the connection, but this looks a lot like that, because this is that x0. You see that? It looks a lot like this one. Wouldn't you agree? It is, in fact, the same thing. M times x can be written as w times x plus b. And this w times x is just all of these, right? Broken up into higher spaces. So we do this one when we only have a graph like this, right? 2-dimensional. But if we have higher dimensions, 3, then we add more components. Okay. But keep in mind, this only creates, if we want to plot this, this creates just a line, straight line, right? If we have a function that looks like this, x2, what's the shape of it? Looks like that. It's quadratic, right? If you do 0, is here, and then you do +1, right? Starts to go up, -1 starts to go down. You see that? So if we have a function that looks like that, x3, these are polynomials, right? So they'll start to look probably like that, right? And so on. So the idea is that we need some way. So currently, this function here, the original function of this, so the original, this part here is still linear, but we need to add the nonlinearity. You see that? And so what happens with that is, I'm going to erase all of this. We need one more thing to make it nonlinear. So what we do is we basically take the original y, this y, and now we run it through some function. And the function basically will take the values from y and now map them to some other space. So in essence, it makes them no longer linear, but now function. So for instance, I'll give you this as an analogy for intuition. If we have here, I'm using purple for the nonlinear, right? And I'm going to use red for the linear. We're going to have the same data, and I'll use a different color. So let's say that my data looks like this. Do you see that? That's what my data looks like, right? Now I'm going to use a different color, blue. So this function can only draw lines, straight lines. So is there a straight line that I could draw in this space that would give me perfect classification with no error? No, right? Because I can do that, and I can do that, and I can do that. But I'm always going to have some errors, right? So there's going to be some that are on one side or the other. So a straight line cannot give me perfect separation. However, over here, actually, I didn't need to draw this. So over here, if I take the y and I run it through some function, now I have the power to create other things beyond straight lines. Do you see that? So I can create polynomials. You see that? That's the intuition with neural networks. That's it, literally. That in linear models, you can only create straight lines. But with the activation functions, you can now approximate other shapes. You see that? And so a neural network is nonlinear because it can do this. Now, is this actually a good thing? It may not be, because remember that your model learns on training data, but your training data does not include all the data in the world, right? It's only a sample of the population. So it could turn out that this is too much of an overfit for the training set. And when you apply this model to the test set, it's not exactly like this. So it's actually not great. But what I'm trying to say is, in essence, you want to avoid overfitting. So maybe the best solution is neither the straight line nor this blue line, but instead, let's use brown, something that is a little bit more like that. You see that? You see the difference between these three? It's like a compromise. So the yellow is the straight line. It's a linear model. It will have a lot of errors. The blue line is perfect for the training model, but it's overfit. It's too much. Whereas this one, this curve, is kind of somewhere in between. And that will probably minimize the number of errors. Do you understand the intuition? So at the end of the day, neural nets are really this game, intuitively, right? That you don't just want to do straight lines like this. You don't just want to do polynomials like that. Instead, you want to find something generic in between the two that can give you the results. Okay, and that's what neural nets are. Going back to the and I'll wrap up with this for today. Going back to Minsky's XOR problem. So Minsky, if you remember, said, solve a problem like this. I think this is the XOR, actually. Right? This is the intuition. The perceptron couldn't solve this, right? Because you needed that to be able to solve it. But the neural net, what it can do is it can approximate this. How does it do it? The best intuition I can give you about that is that it does it like this. That it just does it like this. think of it this way. The model in this space is going to use some specific architecture to build a bigger architecture. So it uses something called a Relu activation, which kind of looks like that. It's like a little hockey stick. So you start then basically putting in little hockey sticks. And then eventually, oops, they get connected and they kind of simulate the architecture. You build it kind of like that. You see that? That's intuitively what is happening. All right, so you start to create these boundaries based on the model itself, okay? And so anyway, so that's the idea. Hopefully that made sense. So you start with, this is the original perceptron. You start with the inputs, you have the weights. That's a linear sum, very much like this one, except that that's only linear. You still need to approximate something beyond linear. So you run it through an activation function, which you can see here. And then that allows you to have better performance, okay? All right, so that's, we're gonna stop here for today. We went over the history of neural nets. I'm done with that. And then on Wednesday, I'll go over now the perceptron more formally, kind of pick up where I left off here, and then we'll just code it up and do our, in NumPy, we'll create the perceptron for some data. Make sense? All right, that's it.
So do you think if Minsky didn't disprove that, they would have worked more on machine learning to be more effective?
Well, if you think about it, Minsky he said two things, right? That it wouldn't work with one single layer, but with multiple layers it would. But if people just misunderstood the word. Yeah, they read the headline, exactly. And they just didn't really dig into it and then just.
Right. So it isn't really his fault.
Yeah, he's the. All right.